Hi, I'm Thomas Lee, an undergraduate studying computer engineering at the University of Florida, as well as a member of the University Research Scholars Program. This program has given me the opportunity to begin conducting research with the Florida Institute of Cybersecurity and allowed me to explore my interest in electronics design. Not only have I learned about the design and manufacturing process, but I've also learned about the ways electronics can be compromised. My focus has been on fighting these risks, specifically with the Trojan scanner, a new process being developed to improve hardware security. Today, many companies have outsourced the manufacturing of integrated circuits to offshore foundries, which saves money on fabrication costs. However, passing along the design of these ICs outside of the design houses can introduce the risk of these designs being modified, such as to insert a hardware Trojan into their production chips. Much like a Trojan computer virus, a hardware Trojan hides a malicious payload behind an IC's normal operation, with the potential to leak data, allow external control, or even cause the chip to fail. Because of the high risk posed by these Trojans, the need to identify malicious chips is important to maintaining security. However, since a Trojan is designed to function without being noticed, they are difficult to detect electrically, they are hard to activate manually, and often too small to detect in this way. Often, a full reverse engineering is required to be fully confident in their presence, a long process requiring months of labor and the sacrifice of many samples. The Trojan scanner aims to be a more balanced detection method by combining the reliability of physical chip inspection with machine learning to speed up the process. Since the scanner relies on images taken of a die's active layers to identify changes, the first step in the Trojan scanner process is to expose them so they can be properly accessed. The die is first removed from its package, either mechanically or chemically, and then is grinded down and precisely polished from the backside to expose specific layers. After the sample is prepared, the exposed layers can then be imaged with an electron microscope, which focuses an electron gun across the surface of a sample, then collects the electrons as they are returned back to produce the image with higher magnification than a traditional light microscope. Electron microscopes have a wide variety of settings that can affect the quality of the final image, such as beam voltage for the depth of electrons or dwelling time for exposure. Some of these settings can also affect the time needed for the image to be taken, which can range from seconds to days. One key task for the Trojan scanner is to find a good balance between image clarity and imaging time, requiring a compromise in quality. Since this compromise results in obscured images, the Python language and computer vision tools are used to improve them in the preprocessing stage. Image equalization, Gaussian blurs, and median filters are applied to smooth the edges of logic gates and obscure static, making the different elements more distinct. Finally, the processed image goes through a threshold process, producing a binary two-color image that clearly shows the layout of the IC's logic gates. The Trojan scanner itself is trained on layout images divided into segments. You can learn to classify segments into their different gates. When given one layout to compare to an unmodified golden layout, it uses this ability to identify and flag specific sections where it detects a change, possibly signifying that a Trojan is present in the IC. So far, the scanner has been fairly effective at identifying layout changes, with a high recognition rate and a low false positive rate, even for less clear images. Although the scanner is still being improved in many ways, such as in the image preprocessing stage, once it is perfected, it has the potential to be developed into a new commercial process for detecting hardware Trojans, saving time and money for companies while adding a new layer of hardware security for all users. The research program has been a great learning opportunity for me, introducing me to advanced topics in electronics early and giving me some of my first experiences in the research process. My time spent at the Institute has been a great starting point for my freshman year, and I hope to use what I have learned to continue helping in research for the rest of my time at UF.